Hello students, welcome to week 2, and I hope you're all doing well. I'm happy to be back in the classroom for you. Just a couple reminders of things I've noticed. You don't have to work on things on a particular day. You can work on it any day of the week. I know some of you are looking at the Zoom schedule kind of grid and think this is the day I have to work on that class. You can work on any class you want, whenever you want. Get work ahead and all that, however you want. All right, let's get to our second unit. And our second unit is the electromagnetic spectrum. That's light. And I'm going to try to respect your time, so I'm just going to try to push through and spare you some of the other things that I might normally say. Just remember that God sends us His Son, just like the sun sends us light, and that's how we know the sun is there. This Bible verse does a great job of using light to say, hey, look, if you've seen the light, you've seen the object. And so God sends us His Son. So we don't have to wonder what God is like. What is He? Is He good? Is He bad? Does He like me? Does He hate me? We know because He sent His Son. So we know about things when things are sent to us. So when your light comes to me, I know what you're like. All right. And so this is what we have. All right. Let's talk about light more specifically. So electromagnetic. We talked about electromagnetic energy when we were in the work unit, and we talked about different forms of energy. There were 6 forms, 6 masks that energy wears, that it presents itself to us. And electromagnetic was one of them. Light has an electrical quality to it, and it has a magnetic quality to it. And so it's 2 fields playing off of each other. An electric field, which is going to be the purple one, and a magnetic field, and they're like 2 cousins that play with each other, and they egg each other on, and they're as one pulls one way, the other pulls another way, and so you know about electric fields, like static electricity. You felt an electric field. You know about magnetic fields because you've worked with magnets. Those 2 fields are related, and the one field can make the other field, and the other field can make the one field. And so what happens is what light is it's one field growing and it builds the other one. And then they pull in on each other, and as they do and they grow each other, they push each other forward. I'm sure someone could go far more in detail than that, but that's basically what light is. 2 fields playing with each other. The next unit we'll learn all about electricity and magnetism. We're going to take those 2 cousins and split them apart and learn about just electricity and just magnetism. But when you put the 2 together, that's light. How is this light born? How light is born, whether it's on your iPad screen or a candle or a light bulb, or the sun making light, or that light box over there making light, the video projector making light, is you have an atom, and the electron going around that, and then the electron, you get that electron excited, which means you're going to give it some energy, and when you give that electron some energy, it jumps to a new energy level. It jumps to a higher orbital. When that electron jumps to a higher orbital, think about it like this. As you're bound up in your house at home, and you get a little bit of cabin fever, and you're starting to get too much energy for inside, Mom says, go outside. Go outside and play. And so you go outside with your extra energy, and you run around in your bigger yard, and you run around, and you let off your energy. But eventually, Mom and Dad say, time to come in, it's time to eat. You have to leave the energy outside, though. The whole point was you left to get rid of that energy. So when this electron, it's time for it to come back home to where it started in that first energy level. When it falls back, it leaves the energy that it had and outside. That energy can't be destroyed. It has to go do something. It has to stay energy. Well, this electron's not going to be holding on to it anymore, so it leaves as a burst of this light. So something comes along. It might be heat. It might be electricity. Some form of energy gives this electron a little extra boost. It jumps to a higher energy level, plays around outside, time to come home, and then delivers that energy. So it started off as one form and then leaves as light. So that's why we send electricity through light bulbs. That's why when the sun's so hot, it's taking those electrons and pushing them out, but then they fall back in. So electrons, they jump out. So with a fluorescent light, we're electrocuting the gas in the fluorescent light, and the electrons jump out and they fall back in. and then we electrocute it again, and the electrons are going like this. Every time we electrocute it, it goes like this into the higher orbital, and then it immediately, right after, falls back to its original orbital, its sort of stable location, but the energy has to go somewhere, and so that's the light. All right, how do we know light looks like this? Because when I look at light, I don't see this, right? I see brightness. I don't see this. I see colors. I don't see that. So we're going to take a look at some other things about light that say, how do we know it works like that? What kind of wave was that? It's a transverse wave. Now light travels fast. It's not instantaneous. It does need to travel. That would be one of those things that had to be discovered, that light travels. It's not instant, but it feels instant. 3 times 10 to the 8th meters per second. So if you wrote it out longhand, you can see that's 8 zeros after a 3. So 300 million meters per second. I think that's like 7 times around the Earth. So it's pretty fast, especially distances where you and I are concerned. But when you start dealing in longer distances, then you start noticing there's a lag. When the signal has to travel up to the satellite and back down to the satellite, there's going to be a little delay. When we watch the sun, when we see the sun outside, that light is 8 minutes old. It's 8 minutes stale. I mean, it's still full of all the energy. None has been destroyed, but the light has already been produced 8 minutes ago. If the sun blew up, we wouldn't know about it. We wouldn't see it for 8 minutes. And then stars that are even farther away, that's where this meme comes from, or whatever you want to call it. When the stars are even farther away, then it could be, you know, in a greater span of time, a long time away. The neat thing about astronomy, different from every other science, all the other sciences try to guess what happened a long time ago, look for clues. But with astronomy, you're actually seeing what happened a long time ago, because it's like it took a movie of itself, and then it shipped the movie over to us, and then we can watch the movie after the fact. So if a star blows up, we're not watching that star blowing up what's happening today. We're watching what happened a long time ago. So astronomy is unique. Astronomy is unique. Very cool like that. All right. Polarization. So now, how do we know that light travels as a transverse wave? Why not a longitudinal wave? I mean, there's no reason why it had to be one and not the other. But it travels as a transverse wave, and we have some ideas why. The number one reason is we have these pieces of plastic here. I'm going to show you this piece of look at this. This is kind of neat. Can you see? Can you see what's happening on the screen here? Maybe if I get this, so it gets bigger for you. Look at that. I'm just twisting it. What? All right. Watch this. This one, boom. Oh, I land. If I overlap them, dark. Here, let me do it this way. Let me put this right here. Am I in your screen? Yeah, I hope I am. So I got these 2 pieces of plastic here. The cool thing is these pieces of plastic have lines. Right now they're vertical. If I twist it this way, well, I twisted the vertical lines to horizontal, but here they are. Do I have a marker here? I write here, hello. All right, I wrote hello. Focus. See that? I'm going to put that over there. Hello. Now, I can make this even easier to see. Let's do that. Okay, I have this other one. Prepare to be amazed. Okay, this is going over top, the second one, with the vertical lines and vertical lines. You can still see it, but watch this. What? What? Oh man, look at that. What goes on? Now I can leave that one, or I can twist this one. What? What goes on? I could, let me do it here. Doesn't matter. See that? Did you look at that? Whoa. Okay, better be careful. I might write a bad word. Okay, so, boom, 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 boom. Here, I can go right over, maybe, I don't know if this will work. Here, I'll go right here. Probably all focusy funny here. And then, what? Here, want me to pass these around? I'll pass these around over here. Okay, just kidding. All right, so we are, let me pull my light box of science back over here, and I'll screen back on. So, where are the glasses here? I have them. Here they are. When you go to the movies and you watch a 3D movie, look at this. So this one's purple. Look at that. One's purple, one's green. What's happening, and I can put this guy with it. What's happening is these are polarized. So these have microscopic, super microscopic vertical lines. And what's happening here is this is how why we think light travels as a transverse wave. Because the light can get through the vertical lines just fine. The vertical light can, the ones that are going like this. Now, the sideways light going like this, still transverse, but it can't get through those vertical slits. The horizontal light can. Because when light is born, it doesn't know which way up is. Some light is born going like this. Some light is born going like this. It's still light. It's still transverse. It's just in different orientations. Some diagonal. But when I send it through the vertical lines, the only light that gets through is the vertical light. And then if I turn it sideways, the only light that can get through is the horizontal light. So if I take vertical light, now only vertical light's getting through. I make this one so only horizontal light can get through, and I put the two together, then no light gets through. It's black on the screen behind. No light gets through. If they're both vertical, then the vertical and the vertical can get through both. If they're both horizontal, the horizontal and the horizontal can both get through both. Why is it purple, maroon, or green and magenta? That light must be coming out of the projector with one color one way and the other color another way. That must just be the way they're producing it out of the projector. When you go to a 3D movie, how do they do 3D movies? Different from when your parents were kids and I was a kid. When I was a kid, they made two movies for you to watch, a red movie and a green movie. They wanted one movie to go in one eye and the other movie to go in the other eye. How did they stop both movies from going into both eyes? They put the red plastic over one eye and only the red movie could get through that one, and then the blue or green movie could get to the other eye. And then your brain put the two different movies together and they were off just a little bit so things looked like they were closer than they were. Then they got a little bit more fancy over the years, and the way they got the movie split apart, because it was kind of sloppy with the colors to do it that way. But the way they got around that was they made a vertical movie, all vertical light, and in a horizontal movie, the light would all come out of the projector horizontal. Same movie, it's just they shot the light out so the light were all one way or all the other way. And then you put your glasses on when you go to the movies, and then this eye only lets one color of light through, and the other eye lets the only other, I shouldn't say color, but orientation of light through. I don't know if that makes sense, but you can filter out the lights. If light traveled longitudinal, it would have gotten through both. It would have gotten through both. It wouldn't matter which way you put it, because it would be moving in a sort of a straight line right through both fences. But because we can block it, we say, with vertical lines or horizontal lines, we say the light probably is traveling with vertical lines and in a vertical manner or horizontal manner. And the only wave that's like that is transverse waves. So all that just explains what polarizedness is, and that light probably is a transverse wave. What does polarized light have any purpose, any usefulness? Yes. One is going to the movies. Another is when you're driving or fishing and there's a glare on the road or glare on the water, you're a lifeguard, you're fishing, you want to see the fish, but you see the glare. When you have glare, that's coming off, the light hits and comes off horizontal. So if you could put on vertical lenses, you'll just block all that horizontal light. It's just gone. It's not darker, it's just gone. And then you can see all the regular light. And the fish or the person that's struggling in the water and jump in and save them. This picture shows it well. Because this light is vertical slits, the horizontal light doesn't get through, but the vertical light does. If I twisted these glasses, well then the red one would get through and the blue ones wouldn't get through. So, if you're driving with your polarized sunglasses, you just look for the sticker that says polarized on it. There's no glare on the road when I'm driving with my polarized glasses, unless I go like this. And then all of a sudden I get glare, because now I'm letting the horizontal light through. All right, you'll read the book and it'll make more sense. Photons, we like the word photons in our science fiction movies, photon cannons in the James Bond game, photon torpedoes in Star Wars. Photo means light, photograph. All right, a light picture, photograph, light picture. All right, a photon is a packet of light. And when light is born, it's released in certain packages, certain quantities. When you think of it like a six-pack of light. When you have a six-pack of Coca-Cola, it comes in sixes. Think about if somebody walked out of a grocery store with Coca-Cola, and you're watching how many Coca-Cola cans do you have in your cart? How many in your cart? How many in your cart? What would you notice? We'd all be buying different amounts. But this person has 6, this person has 18, this person has 24, this person has 36, 48. What are you noticing about all of these quantities of Coke? They're all in multiples of 6. Yes, you can buy a Coke individually, I know. But Coke and Pop seems to come in multiples of 6. So if I had never seen Coca-Cola before, I would quickly figure out that it comes in, for whatever reason, 6s. Light comes in 6-packs too, called photons. Whether you're burning a candle or the Luxor light at the top, it's going to come out in a multiple of what a photon is. They're releasing these packages, these packets of light. So when people were measuring light, they noticed certain quantities, certain multiples coming up. Somebody put it all together and say, why is it this amount and this amount, but never the in-between amount? It must be being released, born in packages. It's called a photon. All right.